There's something called the cutoff ratio that's used in understanding diesel engines. And the cutoff ratio has to do with the ratio of these volumes. So the R sub C is V3 over V2, which is specific volume 3 over specific volume 2. And that's R sub C. And so what it is, it characterizes, in an actual engine, it characterizes the length of fuel injection. So the cutoff ratio means when do you cut off the fuel injector from injecting. And so that's where it comes from. So this cutoff ratio, but we do use that to describe the cycle. So the cutoff ratio, R sub C, if I substitute in here, is 0.1622 divided by 0.0538. And we have that R sub C is equal to 3.01. And now, let's look at the process. So we've got up to state 3 and we described the cut. So now what we want to do is go from 3 to 4, which is our reversible adiabatic process again. And recognizing that V4 is equal to V1. So the process 3 to 4 is PV to the K, reversible adiabatic. So I have that T4 over T3 is equal to V3 over V4 to the K minus 1. So T4 is equal to 2740.8 times 0.1622 divided by V1, 0.861 to the 0.4. So I get that T4 is equal to 1405.7 degrees K. Notice that I'm using K of 1.4 all the way through here. So we see that the temperature is higher. So when they talk about the air standard hot cycle where we use the lower value of K, when I had these temperatures, if I wanted to create a better model, I could use K of 1.3 when I have high temperatures, K of 1.4 when I have lower temperatures, but our purpose right now isn't that, it's just the overall understanding. So P4 is equal to P3 times V3 over V4 to the K is equal to 4850.7 times 0.1622 over 0.861 to the K 1.4. So I get that P4 is equal to 468.6 kPa. So now we've gone all the way around the cycle. Oops, we haven't quite. I got ahead of myself. I have to go from 4 to 1. Wishful thinking. So the process from 4 to 1 is V equals C, or specific volume is equal to a constant. So we have that, and it's Q out. So Q out is equal to U1 minus U4 is equal to C sub B T1 minus T4. So Q out is equal to 0.7176. T1 is 300 minus T4, 1405.7. And so we have the Q out is equal to minus 793.4 kilojoules per kilogram. W net is some Q. So we have 1840 minus 793.4. So we have W net is equal to 1046.6 kilojoules per kilogram. And we can find the thermal efficiency and the mean effective pressure. So we'll do that next. So the thermal efficiency is W net over Qn is equal to 1046.6 over 1840. So the thermal efficiency is equal to 0.569. In the mean effective pressure, just so we have another comparison, the mean effective pressure is W net over V1 minus V2 is equal to 1046.6 divided by 0.861 minus V2, 0.0538. And so we have that the mean effective pressure is 1296.6 kPa. So we have that. And now what I want to do is to look, just as we did with the Otto cycle, to look at some extensions that we could add on to this. And part of it is that these extensions can be used for both engines typically, but now it just becomes a way to expand on what we did. So very often, you're given an engine displacement information info like the specific volume is 2.5 liters. So people talk about having an engine that's 2.5 liters, 3.0 liters, whatever. And what that's talking about is V sub PD. So that's the sum of all the pistons, the displacement volume from all the pistons. And we had that R is 16, so we have that. And let's see if we can find the heat added per cycle. So just as we did before, and we had this, so it's a different way. Last time with the Otto cycle, we had bore and stroke. Here we're going to start off with piston displacement, V sub PD, and the compression ratio, both of which are known. And now let's see what we can do in terms of this. So V sub PD is equal to V1 minus V2, and we know that's 2.5 liters. And V1 over V2 is equal to 16. So V1 is equal to 16 V2. And suddenly I can solve for V2. And I get that V2 is equal to 0.1667 liters. So that gives me V2. So V2 is 0.166 liters, so V1 is the V sub PD plus V2. So I have 2.5 plus 0.1667. So this is equal to 2.667 liters. And now I can find the mass of air. So I'll be able to find the mass of air in here because the mass of air is the mass that occupies. So I have this piston here. At state 1, the mass of air goes from here, from 0, all the way to V1. So a common mistake is that people use the piston displacement to find the mass, and that's incorrect. You need V1. And so M is equal to P1 V1 over RT1. So this is 100. Now I need the volume in cubic meters, 0.00267 cubic meters. So there are 1,000 liters equals 1 cubic meter. 0.287 times 300. So we have that the mass is equal to 0.0031 kilograms. And Qn is equal to M times little qn, W net is equal to M times the work per unit mass. So we have that. And how do we get the Qn? Qn is equal to RFA times H sub RP if modeling actual engine. So one of the things is we need the fuel-air ratio, and that'll give me the Qn value. And in actual engines, R sub C is, let me see, is less than or equal to 10%. And so what happens is that this is where the fuel is going in. And if I have the injection process go longer, I'm going to have unburned fuel because there isn't enough time for the combustion to occur to burn all the fuel. So then I'll have sooty particles coming up. And so I'll have that. So it's limited to 10% of the stroke or less. And the thermal efficiency, for people who love equations, is 1 for its air standard diesel. It's 1 over R to the K minus 1 times R sub C to the K minus 1 over K times R sub C minus 1. And this is equation 1315 for people who like equations. I find it easier just to find W net. And for homework 13.1, 13.5, 13.6, 13.9, 13.11, 13.13.